With its promise of super-efficient power transmission and storage, levitating vehicles, ultra-fast computers, and a revolution in electronics, superconductivity is seen as a holy grail of physics. To fulfill such potential, however, superconductors need to work at temperatures achievable outside the laboratory. To this end, Chinese physicists Zhongxian and Chen Xianhui have made important breakthroughs. The phenomenon of superconductivity was first observed in 1911 by the Dutch physicist Heike Kamerlingh-Onnes. He noticed that the electrical resistance of mercury disappeared abruptly when it was cooled to a very low transition temperature of -269 degrees Celsius, allowing current to flow with no loss of energy. Over the years that followed, other elements, inorganic compounds, and alloys have been found to behave in the same way. To bring superconductivity into everyday life, scientists have been searching for materials that become superconductors at higher transition temperatures. In 1987, Zhongxian discovered a cuprate superconductor with a transition temperature above the boiling point of nitrogen, or -196 degrees Celsius. Cuprates are materials made up of two-dimensional sheets of copper and oxygen atoms, sandwiched between other kinds of atoms.
同氧化合物超导体的结构可以分为两部分，一部分叫做导中层，另一部分叫做载流子库层。当载流子库里的载流子转移到导中层上，导中层金属化，就可以实现超导。现在科技界多数认为，在导中层中，电子之间通过磁交换作用产生吸引，导致电子配对凝聚，从而产生超导。
Chen Xianhui's research has focused on a second class of high-temperature superconductors called ferropinictides. First discovered in 2006, they are based on iron instead of copper and have a very different structure from cuprates.
The core unit of the iron-based superconductor is the tetrahedral iron arsenic or iron selenium layers, in which iron atoms form a two-dimensional square lattice, while the nictide or oxygen atoms reside above and below the iron layers, alternatively at the center of the squares.
In 2008, Chen synthesized a ferropinictide with a transition temperature above an important theoretical limit for superconductivity, called the Macmillan limit. Scientists agree that there is a great need for a theory that can fully explain high-temperature superconductivity. The work of Zhao and Chen has done much to test competing hypotheses and elucidate underlying mechanisms.
Although we already have two kinds of the high-TC superconducting families, one is the cuprates, one is the iron-based superconductors. The working mechanism behind them remains elusive. It's a great challenge for human beings to understand the nature of the high-TC superconductors.
这个高温超导的机理现在还没有搞清楚，大家没有一个理论上的共识，确实是没有一个能够被大家都接受的理论。随着研究工具的不断改善，我相信会有一些重要的规律性结果出来，理论认识的提升是可以期待的。
For their seminal breakthroughs in the discovery of high-temperature superconducting materials and systematic advancements in elevating the transition temperature, the 2023 Future Science Prize in Physical Science goes to Zhongxian and Chen Xianhui.